Hey guys, quantum computing is not quite here yet.
Quantum key generation and quantum key distribution, however, is here in this 1U form factor.
During SC25, Wendell from Level 1 Techs mentioned this.
And the scientists can run experiments while they're here to see, can we do quantum entanglement over the public switch fiber network?
That was actually the experiment last year, and I can tell you a bit more about that later.
So I thought I would show you a part of the hardware that made the experiment possible. Additionally, we'll see how this equipment can be used to improve your VPN tunnel security by using WireGuard as an example. But first of all, I need to straighten one thing out. The experiment Wendell mentions didn't involve quantum entanglement. It was about transmitting keys generated locally by those devices from Poland to the US over a classical link. The setup used a dedicated post-quantum cryptography secured connection between quantum key distribution and quantum key management system instances in Poland and the US. This blue pizza box right here is a Cerberus device made by IDQ. A pair of such units can generate and distribute fully random keys for symmetric encryption. Just so we're clear, a pair means 2 red units or 2 blue units. You might have been confused by the footage I've shown you earlier. Also, a pair of devices consists of a single Alice and Bob device. Remember that, because those names are very often used in cryptography examples. You put one unit in one location, second unit in the other, connect the quantum channels, and they both output the same keys. That's the theory at least, but in practice things work a bit differently, and we'll get to that in a minute. So, how can actual client applications make use of those keys? For example, they can use ETSI-014, which is a protocol for REST-based key delivery. You can literally use curl to grab your keys if you really want to. But wait, I said symmetric encryption. Wouldn't using the same key for both encryption and encryption be trivial for a quantum computer to break? The short answer is nope. Quick disclaimer before we go further. I am not a mathematician nor an expert in the quantum field, so my explanation may be oversimplified at points. You can always correct me or discuss further in the comments. Our current mainstream way of encrypting data, for example for HTTPS, uses asymmetric encryption where a pair of keys is used. One key is used for encryption and another for decryption, so-called public and private keys. Public keys are derived from private ones, and to be specific, single public key is derived from single private key. The problem with this method is that it fundamentally utilizes a product of 2 prime numbers and relies on factorization being computationally difficult for classical computers. On quantum computers, however, this can be done pretty easily using Shor's algorithm. Developed back in 1994 by Peter Shor, it lies dormant waiting to destroy our modern world. Back in my student days, I remember one of the professors saying that the quantum computers may not be here yet, but the moment they appear, we have an encyclopedia of algorithms ready to run on them. And I always found it funny. So, we've established that asymmetric cryptography is easily cracked by quantum computers. But there is a way of making sure your encrypted message is uncrackable. Simply generate a random sequence of bytes as long as the message you're trying to encrypt, and XOR your message against it. Then, send the message over a public channel and hand over the key in person on a USB stick. Since the encryption key is truly random and has the length of the message, there are no clues on how to decode the message via any sort of analysis. And the key you transmitted by hand, basically by a medium incapable of tapping into unless you were beaten up or mugged, so your key couldn't have been sniffed. This is just a general example, but I think it highlights 2 important issues that this device solves. First, a truly random number generation. Pure randomness isn't easy to achieve, especially in discrete computer systems. Most of the random numbers the computer can spew out are only pseudo-random and rely on the so-called seed value, which is most often taken from the current time. But quantum physics is fundamentally random. There exist processes whose unpredictability is based in science and can be proven. The other problem is a secure medium for key transmission. Even conventional fiber transmission can be tapped into and stored by man-in-the-middle attacks without anyone noticing. It is possible to capture the traffic and then replay it in unchanged form. This is not possible, however, with quantum-based channel for transmission. Even if the attacker captures the traffic, it is not possible to replay it without changing some attributes. A pair of such devices solves both of those problems.
What's important to remember is that those devices, the QKDs, are not encryptors in themselves. They generate and distribute keys so that other applications can use them.
Notice this port called Quantum, which accepts SC-PC fiber connector. It is used to form quantum channel between Alice and Bob units. It is also worth mentioning that communication here is one-way only, meaning only single device has the hardware to emit photons and another one has the photon detector built into it. The RJ45 ports are used to provision dedicated links for IP-based management and key delivery. And the SFP port right here is a port called service channel. It is used for an additional required communication between Alice and Bob devices. The rest of the ports are used mostly for building more sophisticated topologies. So, for a minimal, simplest working deployment, you need to connect quantum channels between the devices using a dedicated dark fiber. The service channel, ideally also a dark fiber, since this is not using Ethernet-based protocol. And the management interface, one of those, so that it can also communicate with centralized directory software. And the interface for the keys, obviously, because you have to read them somehow, right? But before I go any further, there is one more interesting aspect of these devices. I have set up SNMP-based monitoring, which gives me information about the complete status of those devices. But what do you even monitor? What do you look at with quantum devices and service channels and stuff like that? Well, let me take you to my Grafana dashboard. There are three key parameters at play here. Visibility, quantum bit error rate, often abbreviated as QBER, and key generation rate. The first two reflect on the quality of your connection and depend on many physical factors, such as the quality of your fiber, signal attenuation, but also some of the fun stuff like how much light is shining on your quantum channel link. Yeah, you heard me right. Very bright light that shines directly here or just on the fiber in general can introduce additional photons in your quantum channel and produce more noise, which in result produce more error. The visibility and QBER also reflect on how many keys the device can generate and transmit. The visibility is quite important, as it shows the level of interference between successive photons arriving from Alice to Bob. QBER shows what is happening with the physical optical link. Any influence and interaction with the fiber will result in QBER increase and trigger alarms. These QKD devices are sensitive to physical fiber strain, bending, stretching, stuff like that. Here you can see the moment I fiddle with the attenuators on the quantum channel, and the visibility rose on an average by 0.02 points, but the key rate increased by more than 1,000. Okay, we have the most important theory behind us. Hope you're still with me, because now is the time for a practical example. The director software I mentioned earlier is used to upload X509 certificates to the nodes in order to authenticate clients asking for keys.
Okay, so let me show you the actual demo of how this thing works. So I have two servers installed in Site A and Site B respectively, where the Alice and Bob units are, Quantum 1 and Quantum 2. And like I said, in the directories on those servers I have certificates for authentication and my getKeys script. So let's look inside my getKeys script. It is a fairly simple script where I have just some variables declared for convenience. Basically the node IP address, the consumer name, which is connected to the way you configure consumers on the server's devices, the URL filled with those variables, and the curl command itself. As you can see, it is a simple curl command with the certificates defined and our content type being defined as application JSON with post type of request. And when we execute that, we will see that the response is also a JSON type response with key encoded in base 64 and key ID. So now what happens is that on the other server, we have a very similar setup with our certificates and with our get keys script. So let's see. And this script is very similar with one slight difference. Mainly now we can pass it the key ID, and our curl command reflects that we are also asking for key ID, which is defined in the payload. And the other Cerberus unit, which is in the other side, should respond with the same key, basically connected to that key ID. The small note here is that you cannot wait indefinitely before asking the other unit for that key ID. You have to do this in sensible time frame. Also, another note is that the key ID you can pass through, basically, I want to say public channel. It doesn't have to be passed very securely, because by definition the environment in which you have your QKD Cerberuses installed, it should be trusted environment, right? Let me grab another key. Let me copy that key ID, and our side B responds with the same key matching that key ID. So as you can see, it's fairly simple. It's not that complicated once you get the hang of it. Let's get back to the video.
But now, I mentioned that you can integrate it with WireGuard. And once again, it's easier than you may think, because WireGuard was designed with quantum security in mind. The secret lies in pre-shared key, the PSK. In addition to private public key pair, WireGuard uses the PSK to further encrypt payloads. When not actively used, the PSK defaults to an all-zero string of 32 bytes, and it is used nonetheless, just as this zeroized value. You can obviously use the PSK without any of that fancy hardware that I have here. Just generate and share it safely. For example, like I said, just write it to the USB and copy it to your peer system manually. But if you want to automate the process or rotate it periodically, well, Arnica is a project dedicated to bridging the gap between WireGuard and ETSI-based devices, generators, whatever you call them. It pulls fresh, truly random keys from the Cerberuses via ETSI API and pushes them into the WireGuard interface. This is advantageous because even if your PSK gets compromised, further communication is still saved after the key gets rotated. Idiot.
Oh hey, I didn't expect you here back so soon. Well, for the Arnica, it's also really simple. So, similarly, after you grab the project from the GitHub, you have to build it. Thankfully it's in Golang, so the build process is pretty simple. And after you have your Arnica binary, I have this helper script called start that helps me start this whole thing. And as you can see, it is pretty similar to the test thing that I've shown you earlier. So I also have my IP address of the node, my consumer name, and then I export the certificate paths, the listening address, the interval on which I want to have my keys rotated, the URLs, the name of my WireGuard interface, and my WireGuard public peer key, and I just start the solution. And this has to be done on both ends of my WireGuard tunnel. So similarly here I also have another start script. It's pretty much the same with respective options changed, like another peer public key. And also it starts. So I already have this running. So if I go into Tmux, you can see that it is configuring and receiving keys and is configuring the WireGuard interface. So Arnica is running in the background and my interfaces look like this. So this is my WireGuard interface, as you can see. And if I show you pre-shared keys on both ends, you can see that this value is the same, F9, as here. And now the tunnel is encrypted with rotated key that is being handled by Arnica. So I'm not sure, yes, enough time has passed, so now we have another key here. And corresponding key has been rotated here on the other end of the tunnel, which is really cool and, like I said, surprisingly easy.
I was surprised you can so easily integrate this cutting-edge piece of hardware with WireGuard. There is one more interesting network use case that you can do with this, but I'll save that for another video, so shamelessly I'll say subscribe. It is, to be honest, really simple to deploy once you get the hang of it. Majority of the time is spent thinking on how and where do you want to connect it and install it. Some interesting issues arise, like the quality of the quantum channel or the light shining on the quantum channel interface, like I mentioned earlier. But get this, I've also heard of ideas on how to make use even of that. Depending on where your fiber runs, you can use the disturbances to your advantage. Every noise or change in parameters can be interpreted as, for example, train coming and going on the tracks that are above the fiber canal. And there are already commercial products that do this. It's just that this is yet another way of making use of the infrastructure you need for this thing. Remember that this is still early adopter R&D stuff, and overall we are all pretty new to this. But I am excited as to where this technology might take us. If I get the occasion, I'll try to show you more fun experiments. For now, please leave a like, share the video. This means a lot to me, seeing that the channel grows. And with that, I'll see you next time. Bye!